right, great. Well, and more on the theme of exoplanet discovery, we'll be hearing next from Tomas Stolker about a recently formed giant planet orbiting its solar system scales. So let's see here, forward, back. This takes a minute or two to do the virtual pointer per second.
All right, good morning, everyone. So yeah, I'll be talking about another planet that we discovered. It's a planet that's relatively young, but that has already fully formed, so it's a very interesting object for studying the early evolution of planets and also dynamics on the solar system scales. So this was a long ongoing project, so I really want to acknowledge the excellent help that I got from my collaborators, both on the field-to sphere side as well as the exogravity collaboration. All right, so we all know that from imaging surveys, there's not so many planets at very large separations, and the reason is really that the bulk of the giant planets is probably sitting much further in. So we know from radio velocity measurements now that the peak might well be at separations of about 3 or maybe 5 AU or so for these Ley-type stars. And that could well be related to the fact that planets form more efficiently close to the water ice line, so the snow line. So the region where water starts to freeze out into solids. From imaging surveys, we have fewer planets, but nonetheless, there's this kind of tentative trend seen for intermediate mass stars here in SCO-SEN by Wagner et al., where you see that as we go closer to the star, there might be an increase of giant planets visible. But of course, there's huge uncertainties on the number of planets that might actually be out there at separations of 10 and 30 AU, but it could be that there's still quite a bit of discovery space there for imaging surveys. Now, one system of particular interest to me for studying giant planet formation is HD 135344AB. So this is a visual binary system in SCO-SEN. It's 2 stars separated by 21 arcseconds on the sky, so 3000 AU. And this system is really well known because of the secondary star. It has been studied for at least 3 decades. It has this huge infrared axis, a transition disk, and since more recent years, of course, we also have these resolved detections with a cavity, a vortex, spiral arms, shadows, all kinds of effects that we think might be related to possible planet formation processes. Now, the actual planets that could be causing these features have never been detected, even though, of course, there have been many attempts. So perhaps they're too low in mass, perhaps there's too much extinction, but it turned out to be quite challenging. So then at some point we thought, well, what do we actually know about the primary star in this system? And it turned out that it's just a kind of an ordinary A0 type star. It has a little bit of infrared axis, but there's actually not that much special about it. But then we thought, well, it's an A-type star. There are more giant planets at A-type stars. Maybe it actually helps that the circumstellar disk has already been dispersed. And one other important thing is that we actually know the age of that main sequence star because it's a binary system. So we can somewhat safely adopt the pre-main sequence age of the secondary star as age for the primary star. So then we just ask ourselves the simple question, well, maybe did the planetary system already form at the primary star? And the answer turned out to be yes. So there is a planet sitting there at about 20 AU, at a contrast of 10 to the minus 4 in the age band that we detected here with the field-to sphere. It was not the only source that we had in the field of view. There were 4 other, presumably background stars detected because we're looking in the galactic plane somewhat close in the direction of the galactic center. So this started kind of a long journey of trying to confirm this object by the astrometry, and that turned out to be quite challenging. And the reason is that the background stars were, of course, moving relative to our science target, but the planet was also moving because it was sitting at 20 AU. That was not the only issue. So usually we assume that background stars are stationary, but actually in that part of the sky, if you look at the Gaia proper motions, the stars are not stationary. So we have to take that also into account. So we obtained, over the course of 4 years, 7 measurements, initially with sphere, so that's starting all the way on the right of the figure. And then after 4 measurements, we could kind of rule out by maybe 4 or 5 sigma that it might be a bound planet, but there was still the possibility that it was kind of an unusual background star with high proper motion. So what really nailed it down, and in the end, is that we took these gravity measurements. In particular, I want to highlight these 2 points that were taken several months apart. Now, the error bars of gravity are so small, they're 10 times smaller than the error bars with spheres, so they're smaller than the markers themselves. And that means that with that precision, we can rule out the oscillation that you get from a kind of a relative parallax difference between our science target and the background star. So here you see a background model that we were fitting with a code called backtracks. So the blue model is a model where we force it to the background to a minimum distance of 500 parsec. And you see that that oscillation that we would get here, that's something we can rule out with the gravity measurements, whereas with the precision of sphere, that would not be feasible. So then, since it was not a background object, we of course fitted an orbital model to that with orbitize, and from that we could constrain the orbital parameters. So it's the planet is orbiting at about 15 to 20 AU. It has a low to moderate eccentricity of about 0.2 to 0.5. And you can also tell from this, so we started here on the right of the orbit, and we're now moving counterclockwise. So you see that we were actually quite lucky to catch the planet at 160 milliarc seconds, because currently the separation decreased all the way to 105 milliarc seconds or so, and in the coming 10 years it's decreasing further to 40 milliarc seconds. So that means actually that the coming 20 years or so, it would have been very difficult or maybe even impossible to discover this planet with an instrument such as field sphere. So I think that also makes you wonder what planets we may have missed because we simply looked at the wrong time at a certain star. All right, if we then take all the photometry and the spectra that we collected, then this is what we get. Here, a fit compared with the Sonora Diamondback models. It's a very red planet. It required a low sedimentation value, so it's a very cloudy planet. You see some systematics both in the IFS spectra, but also some systematics in the gravity spectra, and that's really because we're really detecting the source so close to the star, and we're still somewhat dominated by speckles. Now, importantly from this, we can constrain the temperature and the radius of the object, and that will give us also the bolometric luminosity, which we then can compare with evolutionary models that you see here. And then it, of course, really helps that we have this age prior from the secondary star to get a mass, in this case, assuming a hot start formation. And that provided kind of a fully consistent picture with the radius and a mass and a luminosity that are all consistent with the 10 Jupiter mass object at an age of 12 mega years. If we then compare to the population of directly imaged planets that have been found within 100 AU, and probably by now there are a couple of more that could be added to this figure, then we see that it's interesting because it's really one of the youngest planets that has fully formed though. So there's no indication at the moment, there's no circumstellar disk detected, so it's very likely already just beyond that formation phase. So you see here, compared to the other objects, that it has a relatively low age. It has a relatively small age. There it is. And of course, the PDF-70 planets are even younger, but are still embedded. And that really helps that it's no longer embedded, I think, so you can do more accurate measurements on the luminosity, and in the future, perhaps also atmospheric abundance measurements. If we zoom out now to the full system again, it adds another kind of complexity to this already very interesting system. So we already knew that the secondary star had these spiral arms. So this is work by 2 undergrad students who were using the Gaia proper motions to determine which orbits might be consistent with bringing the 2 stars sufficiently close together that it could actually trigger those spiral arms. But now we also have to think if there might actually be an interaction that could, by the secondary star, that could alter the orbital movement of the planet. Of course, the orbital distances are really large, but the eccentricities are not known for the binary system. Now, with Gaia DR4 becoming available by the end of the year, I started to wonder, well, it's a relatively small orbit, so maybe we can actually learn something about the dynamical mass of this planet. So I made a prediction here. So these are the Gaia epochs, or the orbital solution again. There it is. So this is the period during which the Gaia epochs were obtained. So you see it's during a time during which there's quite a bit of acceleration possible. Nonetheless, of course, it's a relatively massive star. It's a relatively distant system. So these are then simulating for the orbital solutions and taking the Gaia scan law and then fitting an acceleration model, the accelerations that you would expect for DR5, right? So this is not even for DR4, but for DR5. In this case, only for the right ascension component, but you see that, well, maybe for 1/3 of the samples, you get a 2 or 3 sigma detection. But in general, for these type of planets, it's not going to be that easy to find them in the DR4 catalog. So that also means that there's still some value actually for doing more kind of blind surveys. Of course, it will be very important because this is going to help to break this degeneracy between the dynamical mass of the planet and the entropy, which is this other diagnostic that will tell something about the formation mechanism. Now here again, also for specifically for HC 135344A, it's a simulation of the completeness that you would get for DR5, and then you see that at 10 AU, you will be essentially able to detect any planet down to 1 Jupiter mass or so. But an object such as HD 135344AB will have about 10 Jupiter masses and is at about 20 AU, so that's already getting more challenging. Nonetheless, to give you an idea of what we should in principle be able to constrain, if you assume somewhat optimistic values on the precision of the age and the mass of a planet, so in this case for 1 Jupiter mass precision and 1 mega-year precision on the age, we should be able to rule out cold and warm star formation mechanisms. And that, of course, will be interesting to do that for a larger sample of companions to see if there's any trends related to distances or spectral types. All right, that brings me to my conclusions. So HC 135344AB is a super Jovian planet that just finished its formation at 12 megayears. It's a very interesting system for studying both early planet evolution and orbital dynamics in a binary system. It also means that planet formation really occurred at 2 different timescales, at the primary star and the secondary star, which is still actively forming planets, as it seems. Testing for common parallax is actually a very efficient way for disentangling orbital and background motion. So in the end, we were able to do that within 1 year, whereas based on a common proper motion, this would have taken many more years. And detecting similar type of planets with Gaia DR4 in SCOSAN might actually be quite challenging, but feasible in some cases. That's all, and I'll be happy to take any questions.
Hey, Thomas, very nice talk. I'm wondering, how did you guys select that targets in the very beginning?
Sorry, can you repeat that?
Target selection.
How did we?
Do the target selection.
How did we do the target selection? It was just a really long shot. We actually had two targets in our target list. There was one other similar system, and we just wanted to give it a try because we spent quite a bit of time working on the B component and just got really curious. So it was really, we were really lucky in that sense. And that actually puzzled me a bit, and I think that was one of the reasons why I was really skeptical that this was a planet, and it took a long time to get convinced and publish it, because we know that there aren't so many planets out there, right? So yeah, the only explanation that I have is that they're at 10 or 20 or 30 AU, we don't actually know so well how many planets there are, and maybe there are a bit more than we currently think there are. Yeah.
Great talk. Thank you so much. I was curious if you have any thoughts on why planet formation is occurring at such different timescales for a system that would otherwise be coeval.
Sorry, I have a bit hard time hearing you.
Oh, sorry. I was curious why you think the planet formation might have occurred at such different timescales in a system that would have maybe otherwise formed at the same time.
Well, I guess one maybe slightly obvious explanation might be that this is a more massive star. We know that disk evolution occurs more faster around higher mass stars than around low mass stars. So that could be one explanation, like photoevaporation that disperses this disk in the end might be faster. Then, of course, if there is a giant planet in this system that could have trapped material on a wider orbit, so maybe that, of course, influences the evolutionary timescales of disks. But yeah, the only explanation that I have is that it's simply a higher mass star. Yeah.
That about wraps us up, but it makes me think about Jonathan's point about selecting the right evolutionary models and what is T0 for a binary system like this. So I think we are ready for coffee break. Did you have any announcements? No. Okay, great. We'll see you all back in half an hour unless all the speakers.